Okay, guys, so let's keep going. I maybe have only 2 videos to go. So today we're gonna cover buoyancy and Archimedes principle. Lots of application in mechanical engineering, for example. So anyway, the first thing you want to understand is that, let's say you have a beaker here. So we do that in a physics lab. So it's a typical experiment. So you will fill that beaker here up to the top to make sure it doesn't overflow. So if it does overflow, you just disregard whatever came out, right? So you wait to sit to make sure the water doesn't move anymore. And then you're gonna have like something heavy like a rock, and you're gonna submerge it, but you have to put it down in the water at a very slow rate, like very, very slowly. So all the water here that's gonna be displaced can be collected into that catch bucket, right? So we can do that experiment, and if you do that experiment, you can show, but it makes sense. I'm going to close this. Make sense? Am I recording? Yes. That the water displaced here, so the water that had overflown, will be equals to the volume of the object that is totally submerged. Okay, won't be the same if the object floats, but if the object wants to sink here, so then the water that is overflowing here, its volume, it's called the volume of the water displaced, will be equals to exactly the volume of the object here. So it makes sense, and as just told you, we always we do that experiment in the lab. It's a cool experiment. You can even do it yourself. Okay. The other thing I want to bring is that if you have an object that is floating, so it's partially submerged, okay? It's not totally submerged. So you still use the same device here, but instead of having like a piece of iron that will just go in the bottom, you are using like maybe a piece of wood, and the piece of wood is floating, but it's still gonna displace some water, right? Now the volume of the water displaced will be equal to the volume here submerged. So it won't be equals to the whole volume of your piece of wood, but it will be the volume of the piece of wood submerged. Okay, so if you want to do some geometry here, that volume here of the water displaced will be equals to only to that volume here. Okay, and that volume is in 3D, of course. Here you're only seeing one side, but here you have an area. Okay, so that will be small h here, and you have an area there. So here you have the same area, but here you have a higher, larger h, and that you have a smaller h, right? So that volume here will be equals to this volume there. Okay, so just to make sure, this will be easier if you understand that. Okay, so what is Archimedes principle? So we talked about buoyancy, right? So each time you have an object in a fluid, so it could be air or it could be water or any kind of fluid, then it will be acted upon by a force up, right? We call that the buoyant force. And I explained before where it comes from. It comes from the delta H and delta P. Okay, remember that when you have a fluid, the pressure here will be higher. So you have a pressure here, it will be higher than the pressure there. So P2 is greater than P1. And remember that delta P equals rho G delta H. That's going going to be your delta H. Okay, so pressure, remember if you have pressure, then you're going to have a force per unit area. So you have a force here, and then force here, and force here, and a force there per unit area. So if the unit area is 4 times bigger than 1, so it's going to be 4 times the force here. And you see the forces here, the total force, the net force will be greater than the force there. Okay, so total force here will be F down, and you have a total force here, F up. So F up minus F down, it's going to be your net force, and that will be the buoyant force. Okay, so any object that is in a liquid is going to experience a buoyant force. So two things can happen. If you have a piece of metal here, of course, it still have a buoyant force, but the buoyant force is not strong enough to balance out the weight. And if you have something that floats, okay, so if something floats here like a piece of wood, what does it mean? Of course, it's a net force equals 0, so that means the weight equals exactly to the buoyant force. Okay, but you all have experienced that. Now, even if you go deeper, of course, you're going to have more pressure here than here, more pressure here than here. But when you do the delta P, it's still going to be rho G delta H. So it doesn't matter if the thing is down there or up there, both of them, it's going to experience the same buoyancy force, right? Rho G delta H. So the buoyancy force, if you do the math, you can do the math. I think I have a slide that goes for the math, and that was Archimedes that figured it out. The magnitude of the buoyant force equals exactly the weight of the displaced fluid, right? So the legend says that that's what Eureka came. You know, when you find something, you say Eureka. Eureka is Greek. And apparently when he figured out this principle, he went naked in the Greek street and he was yelling Eureka. That's the story. I don't know if it is true. And when he figured it out, he was in his bath because, of course, he was displacing water and he was experiencing a buoyant force. And the weight of the water displaced will be exactly the buoyant force. Okay, so what does it mean? It means that any object partially submerged or totally submerged will be equals, will be experiencing a buoyant force equals to the weight of the water displaced, right? So if you look at this example here, so it doesn't matter if it's submerged or partially submerged, okay? If it's floating, you'll have a buoyancy force, right? So here in that case, what are the force acting on this? You're going to have the weight, okay, the weight of the object. And then you have the buoyancy force here, the buoyant force. And then, of course, here you have the tension. You have the tension of the string. But the buoyancy force here is smaller than the weight. If you let go, it's going to sink. But anyway, that object here is displacing water, right? It takes the place of water. So before it came in, you had water here. That water is being displaced and it's overflowing here. If you measure the weight of that displaced water, it's going to be equals to exactly the buoyancy force. Right? So the force here will be equals to the weight of the water displaced. So let's say we don't take into account the container, or maybe it was calibrated, so you don't take into account the container. You know, when you have the container empty, it's going to be at 0. Okay, so here you have the weight of the water displaced. You can measure with a scale, and that will be equals to the buoyant force. Okay, So here I like this picture because it's really showing you it comes. So those drawings come from Paul Hewitt. I talked about his book. You know, he's amazing author. And he wrote that book, Conceptual Physics. So that picture comes from his book. Okay, so here you have the true weight, right? So gravity is pulling on that mass here, and of course the things is pulling back. So that will be the true weight, right? On Earth, the true weight. And the true weight is 3 Newton, okay? Remember, weight is in Newton, mass is in kilogram, and then you have weight equals mass times 10 about. Okay, so that will be the true weight. Now if you dip that weight inside the water, you see that the weight will be smaller, right? Because now you still have the weight down, and you have tension here. So you have the tension there, it's in equilibrium, and you have the buoyancy force there, right? So buoyancy plus tension equals the weight. So you see that it seems that the mass here is lighter, so it's gonna weigh 1 Newton. Before it was weighing 3 Newton. So it's like there was a 2 Newton, pushing up. That will be the weight of the water displaced, and that's going to be the buoyant force. You see here it's in equilibrium, so T, the tension, which is the apparent weight, it's up, plus the buoyancy force is up, equals the true weight. Okay, so the apparent weight in the fluid will be the true weight minus the buoyant force. And that buoyant force depends on how much water has been displaced. So it depends on the volume here, right? So here you have the same volume. This volume equals to that volume. So it's going to be the weight, that's the true weight of water displaced. So more water you are displacing, so bigger volume you get, more buoyancy you get, right? So it means like if you take a piece of iron, like you make a ball, and it's all iron, it's going to sink. Now if you take the same mass of iron, but now you make it like a boat, right? So what's going to happen? You're going to displace enough water to have a big buoyant force that will balance out your weight, and then it can float. So you can do that experiment. You take a piece of aluminum, you make a ball out of it, it's going to sink. You put that in a pan, for example, it's going to sink. But if you make it as a boat, in the shape of a boat, it's going to float, because more water you are displacing, more buoyancy you get. So it all depends how much water you are displacing, right? So the buoyant force equals the weight of the water displaced. So in that case, the apparent weight equals the true weight, which is 3, minus the weight of the water displaced, which is 2. So then you get 1. Okay? So here you have the math, and it comes from the fact that you have more pressure at the bottom than you have at the top, because the pressure depends on the depth below the surface, as we discussed many times. The pressure on the sides here, of course, you're gonna have also a gradient, right? So you do, I said that already, but you see here you have a pressure. So the pressure also here increase, but on the other side, everything is symmetric, right? So they're gonna cancel each other. Even though there is a gradient here, so there is a force per unit area. That's what the pressure is, the force per unit area. So each unit area, you're gonna have force applied to it, but you have the same thing on the other side, okay? So remember, we live in the ocean of air, but because we have, you know, pressure is applied to us in all direction, and inside us we have the same pressure, so everything is balanced. No. Okay, so where am I? I'm here. Okay, so we can we can explain how the things that make sense, of course, but we can show that with the math, is that if the density of an object equals to the density of the fluid, then it's going to be an equilibrium. It doesn't go up or it doesn't go down. Okay, I think I can show you that. So a fish here can control its buoyancy because it has a special bladder. I think they call that swing bladder. So they can fill the bladder with air. So if they fill it with air, they decrease their density. Or they can push the air out, so you go bubble, 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 they make all those bubbles. So the density is going to increase, so they can go down. But of course, I guess they do it without thinking about it, right? They're not going to say, okay, I'm going to bubble up so I can go down, right? So let's say you have a fish here. And of course, it's going to displace its own volume in water, right? So that will be the water displace. And the weight of the water displace is going to be the buoyancy force, right? And remember that density is mass divided by volume, or you can write that mass equals density times volume, or you can write that volume equals mass divided by density, right? Yeah. So here, let's take that fish here. Let's say the fish is in equilibrium. You see that you're going to have two forces. You're going to have the weight of the fish. Of course, it depends on the density and of the fish. And then here you have the buoyant force, and it's in equilibrium, so the buoyant force equals the weight of the fish, right? So what can we say? We say the weight of the fish, which is mg, equals the buoyant force. So the mass of the fish, mass will be the density of the fish times the volume of your fish times g. And then the buoyant force will be the weight. So imagine you have displaced that much of water, that will be exactly the same volume of the fish that the fish is taking. So the weight here of the water displaced is going to be the mass of water displaced times g. Okay, so that's going to be, that was the mass of the fish. So the buoyant force equals the mass of the water displaced times g. So mass is going to be equals to density. So here we're talking about the density of water times the volume of the water displaced times G. But because the fish is totally submerged, okay, so it's totally submerged here, so the water displaced, the volume of the water displaced is exactly the volume of the fish. Okay, so the water displaced, it's exactly the volume of the fish. So I can cross that out, and you see that the density of the fish equals the density of water. So in that case, it's in equilibrium. But you can do the same thing. What's going to happen now if the density of fish is greater of the density of water? So then you can do back. Okay, so that means the density of the fish times the volume of the fish times G is greater. So that will be the density of the fish. Okay, so that will be the weight of your fish here, and then you multiply on both sides the water, the volume, because this volume equals to the volume times G. So what do we have here? We have that in that case the weight of the fish is greater than the buoyant force. So if you have this, okay, so if the fish can increase its density, so then it's going to go down, okay, because you have a net force. That's your fish. You know, it's the fish we find in supermarket, the fish stick. So the weight here is greater than the buoyant force, so it's going to go down. Okay, does it make sense? So you can do that by, there's an experiment that you can do, but it has like something here. I don't know where is it. Okay, it has a bladder somewhere. I can fill with air, so the density goes down, or push the air out. I don't know, maybe it's bubble out. I don't know if the bubble goes this way or goes that way. Not sure. But if it bubble out, so then it will sink. Okay. Now, interestingly, the submarine, you have submarine, works exactly the same way, but now they take inside water, right? So they have what it's called the ballast. It's like a ring, a cylindrical ring all around. I'm not sure, okay? I'm not versed in the submarine topic, but it must be like all around. And you can have compressed air. So here you have water, so a lot of water, you increase the density, so you can go down. When you want to go up, the air is gonna push the water out. Okay, so the water is out, so you have air, so the density goes down, so you can go up. Okay, and of course, if you want to sink again, you're gonna make the vacuum, so you're gonna get rid of the water, or you're gonna compress the water again. So here you have a vacuum, so you have less pressure inside that you have outside, which is water pressure. So the water will rush inside again, and you can sink. So that's how it works. Okay, so the whole story with Archimedes was the story with the crown and the gold. So the story goes that there was a king. I don't know which king. You can Google it. That story with the king. Okay, so there was a king, and he asked his craftsman to make a crown, and he was suspicious that it was, and he gave him the right amount of gold to make the crown, right, to melt it and to make it in a beautiful crown. But he was suspicious that his craftsman cheated him. So he asked Archimedes if there was a way to find out if it was pure gold or not. And Archimedes thought about it, and then he came to the idea, he submerged, so he took the same amount of gold, like the same weight, so these two have the same weight, right? And it makes sense to you that if this is not gold, they don't have the same density. Gold is very heavy, so maybe it's part aluminum, maybe inside, and the gold is just on the outside. So then we expect that to have more volume, right? So they submerged, he submerged them, and he was able to show that the crown here was experiencing more buoyant force. That's because it was displacing more water, so it was taking out more volume. So the density was smaller, so it means it was not made of gold, right? So if it was gold, you will have that the mass. So before, you see that mass here, so ρ1 V1 equals ρ2 V2G. So if the craftsman didn't cheat, that will be equals to this, and this will be equals to that. But here he put in water, so what does it mean? That ρ1 has to be smaller than ρ2, okay? And V1 was greater than V2. So that way he was able to show that it was not meant, was not gold. So I guess the craft at the time, you know, they didn't have to go for a trial when you were the king. It didn't end well for the craftsman. I'm not supposed to cheat the king, I guess. Okay, so this is used. I don't know if they do it anymore. You should know better than I do. I know they have today a special scan. I don't know what kind of radiation they are using, so they can tell what's the proportion of fat relative to muscles and bones. But you can do it also this way, and you see that fat float and muscles and bone have a higher density. Okay, so if the apparent weight is smaller, so you will weight less. Okay, so you can, using some math here, you can find the proportion of fat. Okay, let's do some problem here. You can stop. You can stop the video and try to do it. So again, I'm telling you my source. My source here for this problem is Paul Hewitt, Conceptual Physics. Okay, he has very smart problem that I like it. Okay, so let's try to answer. So what is given? It's iron. It's made of iron, and you have the density of iron. Okay, so it's given. So in air, so what's the question? It's two questions. One is easy. Okay, listen, I have that. I'm gonna use this. Okay, so here she's holding a barbell here. She must be very strong because 900 kilogram, that's like 2,000 pounds, or like 1,800 pounds. I don't know if it's realistic, but let's say she's really strong. And so it means what's going to be the force she has to exert to balance out the weight. So you already know that from physics 1. So the weight of the barbell, it's going to be 900 kilogram times 10. So it's going to be 9,000 Newton. Okay, and they give you that it's made of iron, and the density for iron is that. Okay, so no problem. So here now she's in underneath the surface. So then the question is how much force she has to apply. So Now, if I look at just the barbell, so the barbell is displacing water, right? So it displaces its own volume, so the same volume in water. So that weight of the water displaced, that's going to be the buoyant force, right? It's the weight of water displaced. So what are the force acting on those barbell? So you're going to have the weight of the barbell. I'm going to WB, and then you have the buoyant force here, which is the weight of the water displaced, and you have, I'm going to call that F Winnie. Her name is Winnie, so we call kind of force. That's what we want, the force from Winnie. And you know that because it's equilibrium, the force from Winnie plus, so up, buoyant force equals the weight of okay, we call that WB, right? So the weight of the barbell. Okay, so we need to find this, so we need to find that, and we need to find that, right? We can, so here we can say that the force from Winnie has to provide, it's going to be the weight of the barbell minus the buoyant force. Okay, so let's do it step by step. So we have the weight, the buoyant force. Okay, so the buoyant force, it's going to be the weight of the water displaced. So it's going to be the mass of the water displaced, so that mass here, times G. Mass is density times volume, right? Because rho is mass divided by volume, so mass is density times volume. So it's going to be the density of water times the volume of water displaced, so that volume here, times G. Okay, but that's going to be equals to the same thing as rho of the water times the volume of your barbell times G. Okay, so to find the buoyancy force, I need to find the volume of the water displaced, which is the same as the volume of your object. And I look back to here, and you cross, multiply, divide, you see that volume is always equals to mass divided by density. Okay, so the buoyant force equals the density of water, which is easy, times the volume of your object, which is the mass of the object, divided by the density of iron, and don't forget G, right? So what do we get? Something very interesting is that the buoyant force, and it's always true when you have a totally submerged object. So the buoyant force will be the density of water divided by the density of your object, which is kidnapped kit. So the density of the object, so the density of water divided by the density of the object, okay, times so mass of the object times G, so that will be your weight. Okay, so this will be the weight of object. Okay, So I want you to write that down somewhere if you are taking a test or just to remember. It's something that you should know, because then it will be faster. You don't have to do all those steps next time. But that works. This is only for submerged. So totally, not partially, totally submerged object. Okay, so the buoyancy force equals this. Okay, we didn't answer the question yet. So let's go back to here. So the force the Winnie has to apply will be equals to the weight of the object. So that will be 9,000 Newton minus rho of the water divided by rho of iron times 9,000. Okay, so you can do the computation. You have the iron, so you can go ahead and do the computation. I just want to keep going here. I'm gonna factor out my 9,000, which is the weight of the object, 1 minus rho of the water divided by rho of the iron. And when you do that, so iron is 7,800. Water, remember water is in 1,000. So when you do 1 minus this ratio here, you get 0.87. Okay, so that means the force that she has to apply is 87%. So it's a 10% less or 13% less. Okay, you understand? So Winnie has to apply a force of 7,846 Newton. Okay, but the interesting thing to remember is that works only if the object is totally submerged, so it displaces its own weight. If it's floating, it's partially submerged, so it's not displacing its own volume, displacing its own volume. Okay, so it only works when it's totally submerged. Okay, so we have this relationship here. Okay, so a very cool problem here. Building up. So if totally submerged, then the buoyant force equals rho of the water over rho of the object times the weight, the true weight, right? The weight in air of the object. Now, if you divide by g both sides, do you remember that the force is the mass times g, that will be a weight, right? So we can say that the mass, if you want, will be, if I divide by g, so then it's like I have a mass here, okay? So it's going to be rho of the water divided by rho of the object, the mass of the object. But this is what you want to remember, but only works when it's only work when it's submerged, right? So here, what's a very cool tool, and remember how we work with units. It's very important that the units are the same on both sides of an equality. So it doesn't have to be kilograms, or it doesn't have to be Newton, as long as it's consistent. So that's a trick that they use in geology. So what they do, they have a scale, and the scale is that's a scale, okay? So they are attached. Let's say you find a rock, and you don't know what the rock is made of. So you want to find its density, okay? So you measure the mass of the rock in air, okay? And let's say you find that rock is 150 grams. And then you're gonna submerge the rock in water. So it's going to be totally submerged in the bucket of water that you have. Okay, so this is water. So you're going to have you're going to have the weight. Here you just have the weight and the tension. Here you have the tension and the weight. And you see that it's less. So it's going to be, how much is going to be? 83 grams when it's in water. So the difference between 150 gram and 83 gram, that's going to be due to the buoyancy force, right? So you have the buoyancy force, and that will be in gram. Okay, so we're going to try to use this equation here. Okay, so you have, that will be what we call the apparent weight. Okay, we remember we talked about that, and this is the true weight. And the difference between the true weight and the apparent weight is the buoyant force. Okay, just remind you, that will be the true weight, the same as here. So here you have W, here you have W, but now you have a buoyant force here, and you have also the tension. So the tension here, that's what you are reading there. Okay, tension here, it's pulling on that, so it's pulling back. So that's your apparent weight. So you can find the buoyant force by doing 155 minus 83, okay, times let's say you 9.8 here. And I'm going to put 9.8 because we are used to the gram, and this is in gram. It's supposed to be in it's supposed to be in kilogram, but you're gonna see it doesn't matter. If everything is in gram, then we are good, okay? So if everything is in gram, we want the density of water to be in gram also. So 1 gram per cubic centimeter. So the volume will be in cubic centimeter. And what do I need? I need to find the rock. Okay, so the buoyant force will be 155 minus 63 times 9.8. Okay, so that will be your buoyant force, times, if you want to divide by 1,000 to have kilograms. You don't need to do it because everything will be in grams. You don't even need a 9.8, but I'm going to just leave that. But now I don't want to do all the computation. I'm going to use this here. So the buoyant force, we know it's going to be rho of the water. That's going to be in gram per cubic centimeter divided by rho of the rock, and I did all the demonstration before. That's also be in gram per cubic centimeter. Okay, so we got here, see, can cross that out, times here the weight, the true weight. Okay, so that will be the weight of the object in air, so that's going to be times 155 here. Okay, so here I have 155 times 9.8. Okay, so this is given by my experiment, except of course you can divide by 1,000 if you want, and then here of course you divide by 1,000 as well to have everything in kilograms. Do you understand? So here that's given by the experiment, that's going to be the buoyant force, and we just show in the last problem that the buoyant force, you have to take the ratio between the density, you multiply by the true weight. So these are going to be equal to each other. And 155 minus 83 is going to be 72. So we're going to have 72 times 9.8 equals rho of the water, so it's 1 gram per cubic centimeter, divided by rho of the rock, so density of the rock, times 155 times 9.8. That's why I told you that 9.8 doesn't matter, it's going to cross out. Now, if you want everything in kilograms, you have a 10 to the negative 3 here, but you have also a 10 negative 3 here, so it crosses out. So if you feel more comfortable, you could have, divide by 1,000 here, divide by 1,000 here, you will be in. Okay, so then from here, it's easy, right? So you just math, so 172 equals 155 divided by rho, and you're going to find that the density of the rock is 2.2 grams per cubic centimeter. And then you take your, if you are in geology, you have special table and you see that 2 grams per cubic centimeter. Don't know what it is, it could be feldspar, it could be something else, granite. Okay, so you can, that's a very cool application. Okay, so let's do number 2. Okay, so number 2, it's another problem. Okay, it's building up on the fact that when something floats, okay, so when something floats here, you see the buoyant force here, the buoyant force that you have depends only of the water displaced. So it's not displacing the whole boat, okay? It's just displacing not the whole boat, okay? It's displacing only that much of water, right? So the buoyancy force equals only the weight of the water displaced. And you see that because it's floating, so you also have here the weight of your boat. Okay, so you have the weight of your boat will be equals to the weight of the displaced water. That's going to be equals to the buoyant force because it's floating. So this is very important and sometimes it's confusing. So the buoyant force here equals the true weight. So we are not talking about apparent weight anymore, okay? So it's really the true weight, and the true weight equals to the buoyant force because it's floating. We suppose it's floating, and it's equals to the water displaced. Okay? So let's go back to this problem here. Here. Okay, is it still recording? Okay, I hope I can finish everything before someone comes. Okay, so a pie pan, blah blah blah, it's floating on the water, so we neglect the mass of the pan, so it means it doesn't displace much water, right? So we have an aquarium here, you have a pan, but we don't care really. It's so light that we neglect the mass and it doesn't displace much water anyway. So then we put a piece of iron in it. So what matters here, even if the piece of iron is heavy, because the pan is big, it's going to displace, hopefully, enough water. Okay, it's going to displace. So you see it went down by delta H here. So it's going to displace enough water to be able to hold that piece of iron. So you have here, you have the piece of iron here, W, and then you have the buoyant force, and the buoyant force equals to that